lecture is by James Cranch from the University of Sheffield, and he'll speak about how not to define type categories, probably, in HoTT. In HoTT, yeah.
Thanks very much. Well, so the first thing I'd like to say is this talk is based on a paper that's on the archive, and in fact it's going to improve. Both through the passage of time and some nice comments by some referees, this paper will get better at some point. My other promise about the content of this talk is the ACTA code available soon. Indeed, sooner if you email me. That should also answer another question. So I don't understand the differences between various sorts of type theory. So if you have a technical question about which sorts of type theory what I'm doing works in, the answer is likely to be, I did it in ACTA. That's the level of my understanding on the subject. Okay, so what are we trying to do? So Homotopy type theory is supposed to permit representations of interesting mathematical objects. So, I'm a mathematician, I'm interested in categories. I hope I can persuade you to agree that categories are interesting mathematical objects. I wanted to represent them in homotopy type theory. So, goal, categories. And there's some prior art. There's a paper by Ahrens, Kapulkin and Shulman, several of which have been here. So, prior art, paper of Ahrens, Kapulkin and Shulman. I'd like not to write down their definition in full detail, but I will sort of drop a few hints about their definition, just so that I can say what I want to do differently in a bit. So, definition, I'm going to call them AKS categories. That's an abbreviation for their names. So first I'm going to tell you what an AKS pre-category is. And I guess the slogan is an AKS pre-category is the first thing you'd write down if you were trying to define categories in homotopy type theory. So an AKS pre-category is the obvious thing. I suppose I really ought to drop a few hints about what sort of thing is obvious, so I'll go some of the way. So you have a type of objects, and for any two objects you want a type of morphisms. So Hom, so the people who know this definition already are going to sort of complain to me that I haven't written the right thing. I'm going to come back and say the right thing in a second. So yeah, you have a type of objects, you have a type of homomorphisms between any two objects, and then you want to go and you want to shove all the structure of a category onto that collection. So you have identities, and that's going to be, for every object, it's going to be an element of the Hom from that object itself, and you've got compositions. And then that's not yet a category, that's sort of just some weird structure. You've got to impose some axioms, and they're the usual axioms of category theory. And that's a bit of a mess for reasons I'll go on and say in a second. And they deal with the mess by giving an extra axiom, so plus all Hom types are sets. So all Hom types are homotopically discrete. And that deals with various coherence issues that I'll sketch in a sec to do with what happens if you allow more exotic Hom types. And then they go on and they talk about how that differs from being a category. And the observation they make is that this now differs from a category in one regard, namely, you can ask the type of objects what its equivalences are, and you can ask the categorical structure what its isomorphisms are, and you might get different answers from the two of them. So, yeah, two notions of iso or equivalence in such a category, pre-category. Namely, the type theoretic notion of equality in the type of objects equals subscript obj. That's a notion of equality of objects, and you have also categorical isomorphism. And it's pretty quick to check. You get a morphism from the former to the latter. So you get a morphism from equals on objects to isos. And what they do is say, you shouldn't be able to ask a category what its isomorphisms are and get two different answers, so we'll just impose that that's an equivalence. So, further definition, an AKS category is one where this morphism is an equivalence. And I guess this one's the slogan of univalence. It's a categorical univalence axiom. Like the univalence axiom of type theory, it says that two different notions of equivalence or equality should be the same. Okay, and this is a perfectly workable notion of category theory. It seems to work perfectly well in their paper, for example. But there's a lot that you're missing out of when you impose that Hom types should be sets. What you're getting is a notion of ordinary categories, of one categories. You could want so much more. Could want more general Hom types. You certainly could hope that you have a definition of a category and the Hom types could be any type you liked, not merely a set. But this leads you into sort of standard coherence problems, and since I think the audience is drawn from a wide range of backgrounds, I'll spend a couple of seconds sketching the coherence problems that you usually get. So, the usual coherence problems. Well, okay, so you've got to define composition. So, for compatible sets of objects, you need a composition on the Hom types. And that leads you to define GF. I'm going to draw that as a dot. It's not just a dot of data, it's a dot of data for every pair of composable, for every set of composable directions, you've got to give a composition map. But then, when you have three sets of composable Hom types, X to Y, Y to Z, Z to W, that structure gives you two different things. So here's HGF, and here's HGF. And if all you've done is just explain how to compose two homomorphisms, there is no guarantee whatsoever that these are the same. And they should be the same. So you have to give an equality between them. And by the usual sort of representation of homotopy type theory as something to do with geometry, I'll just draw a picture. You give that. And that's an extra data. You're not done yet, because when you have four composable morphisms, or, rather, four composable Hom types, x to y, y to z, z to w, w to whatever the next letter of the alphabet is, then there are 5 different ways of bracketing it. Yeah, w does come after z. It's weird, isn't it? KH, composed with GF, and you can associate that with KH, GF, and you can associate that with KHGF, and you can associate that in turn with KHGF, brackets here, and you can associate that with, what else should go here, KHGF, and we've given a bunch of associativity structures, and they give us edges like this. So by using this structure repeatedly, we can fill in this pentagon. But that gives us a non-trivial loop. If we start here, we can just walk around the circle, get back to where we started, and if we are not luxuriating in a sort of simple situation where the Hom types are sets, this could very well be a non-trivial loop in the Hom type. So we have to fill it in, we have to do something to say it's trivial, and that's further structure, and if I have a 3-dimensional blackboard, I draw the next one up, and that's still a problem, and it never stops. So you have to give an infinite amount of information. So classic mathematics, that done by topologists and homological algebraists in particular, has come up with a lot of solutions to this problem. It's an old problem, and it's been solved since the 60s in various ways. In homotopy type theory, this seems like hard work. So, seems like hard work. Seems like hard work constructively. So I think there are some bright people who are known to be working on it, and they're not done yet. So the question I want to think about is, what can I do for free? So what can I do without bothering to deal with infinite coherence issues? So all the methods I'm going to consider are going to be sort of deliberately, explicitly stupid methods. So, if you see my definitions, you think these are daft, these are too pathetically weak to cope with categories, then that's sort of deliberate. If adjusting for that fact they still seem like stupid definitions, then we have a problem, we can talk about that. But do bear some amount of stupidity in mind. Okay, so is that what I wanted to say? Probably is. Alright, so how are we going to deal with this? And I sort of realised, sort of observation, if you're doing homotopy type theory, there is an infinity category, an infinity one category, a fully coherent object, sitting there for free, with no work. So that is type. You're sitting around, you're doing homotopy type theory, you've got this object of type. So type is a sort of an infinity one category, and it just lives there. You don't have to do any work to define it. There's no structure you have to construct. You just notice the structure lying there. So the objects of type are the type, and the Homs from x to y are the function type from x to y. I'm going to use Agda style notation, so I'm going to use arrows rather than exponentials. And all the other structure that you want, every time you think there should be some structure in an infinity one category, it's just there. You look for it, you find it, and it's pretty trivial. So let's write a bit more. Id x equals sort of lambda x to x, identity objects that the identity morphisms are the identity function. The composition of G and F is the composition of G and F, which in sort of lambda x goes to G of F of x. Univalence is univalence. So I'll sort of write that in a slightly more comprehensible fashion. So AKS univalence equals Blavatsky univalence. That is, if you're hoping that the notion of equality in type should coincide with the notion of equivalence of morphisms, which is the thing you demand for AKS univalence, then the appropriate statement is presumably exactly the statement of Blavatsky univalence. And everything just works nicely. So you try to construct the associative law, and Agda doesn't let you do any work. So you try to write down an object that is, an identity between H composed with GF and HG composed with F. And Agda normalizes both of them for you to lambda x goes to H of G of F of X. Exactly the same thing. And then you scratch your head, while looking at the screen, sort of fearing you're going to have to write down some hideous term, and then you sort of hesitantly type in REFL, and Agda stops complaining. Agda's completely happy with that. And you think, right, the difficulty hasn't begun yet. I'll go up a layer and talk about this. You really can't. Agda doesn't let you. So every time you try to type in REFL, Agda lets you. I don't understand the type theory of Agda well enough to make that a theorem, but empirically, you can spend a lot of time typing in REFL and nothing goes wrong. So, this gave me an idea. Why don't I just spend some time ripping off the structure of type as much as possible? So I'm going to define some infinity 1 categories, and all the hard work is going to be done by type. So idea, define some proper infinity 1 categories where low degree cells are done by hand and high degree cells are done by type.
Does that mean they're also all done by REFL?
Yeah, eventually when you define these things, the proofs you want are going to be done by REFL. So I'll give you a series of definitions for a series of increasingly ambitious meanings of low degree. So we'll give a series of definitions where low degree means less than n for increasing n. And I'm sort of asking you to believe, I think, that type really is an infinity 1 category. And then, in each of these definitions, it'll be obvious that the work is eventually done by type. So you have to argue about the low degree structure, but then the high degree structure really is just structure in type. We'll be able to see that. So I'll give you a few of these definitions. The first one is going to be daft, even by the standard daft definitions in the talk, but I think it's important to give it because I can point at the pattern and have you understand it at the same time. So let's give the first one. I probably ought to look at that while I'm writing it down. Not that, I shouldn't. G That's fine. Okay, so the first definition, which I promise you is completely ridiculous, and you know, if as I'm writing it you think this is a ridiculous definition, don't worry, I'll come back to that point. Okay, so a zero concrete category. At various points in preparing this stuff, I've agonised over whether the natural numbers start at 0, which was the old convention, or -2, which is the new convention. I'm just going to start my naturals at 0. So the zero concrete category consists of obj, which is a type, the type of objects. Obj plus, which is a map from obj to type, and this tells you which type is going to end up coming to the rescue of each object. This tells you, you know, exactly which types we're going to use to get the higher structure from. We want hom, and that's going to go from obj to type, as usual. And then I want something which explains how the hom types have something to do with these sort of representing objects. So I'm going to define hom plus, and that goes, given x and y objects, this gives me a map from hom xy to the map between the appropriate corresponding types. So I've got hom sets, I've got hom types rather, and the hom types I regard as living over the maps between corresponding objects. And then I need some axiom to say they live over it very closely. And in the case where n is 0, my zero concrete category, so I call this conformance, this is going to be a very strong sense of this represented by this, and in fact it's going to be for all x, y, hom plus that x and y is an equivalence. So right, I promised you that this was a ridiculous definition, and of course it is. What I've done is define for you a full subcategory of type in an extremely convoluted fashion. So what I've got is a type of objects. I've got a map from those objects to type, and then I tell you about some hom types, but I needn't have bothered because they're the same as the maps between the representing objects. So this really is just a kind of indirect way of defining a full subcategory of type. So, remark, just a full subcategory of type. And I'm unapologetic about that because I think it's going to be easier to understand the definition if I've written down a stupid version before I write down a slightly less stupid version. But that's not to say that full subcategories of type are completely useless. So there are a lot of them, and some of them are things you want to work with. So I probably wrote down some examples somewhere, or nah, I didn't bother, not yet.
In what sense is it a subcategory?
Yeah, solid point, but I think when people use the phrase full subcategory, they don't always mean full subcategory. So you know, they mean can have multiple copies of some objects. So I see that occasionally in the literature. So I mean, when people say, in classical mathematics, when people say full subcategory, they should mean that there's an inclusion on the objects into the objects of the thing you're taking full subcategory of. But in practice, nobody ever bothers to check, and in a lot of situations, it doesn't make any difference. So I mean, classically, of course, in ZFC and all that, you could replace it by a skeleton, which would be something you could regard as a full subcategory. But if you can't here, I don't care. So yeah, full subcategory is somehow logically not the right word, but it's closer to the right word than anything else I can think of. So I'm broadly unapologetic about that. Okay. So quite useful. You could spend some time, and I did spend some time wondering how many things are full subcategories of type. The answer is there's loads of things that aren't full subcategories of type. For example, don't got much time, so I'll just sort of mention one as sort of cute exercise. The two-element discrete category, two elements, no objects between them, just identity no morphisms between them, just identity morphisms on each, is not zero concrete. And you can prove that internally to the type theory. You give an internal argument why there's no zero concrete category that looks like that. It's sort of tough. But that's a limitation. So, now we've done that, I'll give you a one concrete category, and it'll be helpful to see the difference, because that pattern's going to continue. A one concrete category consists, again, I better not leave anything out. So we've got obj, which is a type. We've got obj plus, which goes from obj to type. Again, each object has this little saviour type that we're going to end up using for its structure. We've got hom, from obj to type. We've got hom plus, which explains the way in which hom types are somehow represented by these. And that again goes from xy. This is the last time I'm going to write this, I promise. To hom xy to obj plus x to obj plus y. Now we've got conf, which is going to be a little weaker. So rather than saying these things are equivalences, I'm going to say just that they're, what do you call it, -1 truncated. So conf says that for all xy, hom plus of xy is -1 truncated. In other words, it's fibred in propositions. In other words, we choose some connected components of the morphisms between the representing types. And then we need more structure. This thing doesn't deserve to be thought of as a category yet, because when we make conf a bit weaker, we need to supply a bit of the structure by hand, and the structure now is that we need to promise that there really are identities and compositions. So we need something I'll call id prime, which says we get the identities from type normally, but now we have to supply them ourselves. So for every object in X, we have an element of the fibre of hom plus at id of obj plus of X. So in other words, this just says we do choose the connected components that have the identity maps in. And similarly, we're going to demand that if we have two components, we've got to choose the connected component that contains their composites. We're not choosing all the connected components, we've got to ensure the connected components we choose are closed under id in composition. So it's a big comp prime, and that says, this is going to be slightly unpleasant, but I'll write it anyway. X, Y, Z to objects, and G in hom Y, Z, and F in hom X, Y. Then, given all that, we have an element of the fibre of hom plus at id on hom plus of G. So if we take two morphisms, we
You can
look
do
at
it
what...
nicer.
Pardon?
You can do it nicer.
Can you? All right.
You can have id, just like in a normal category, just an object, just an object of the home type,
Okay.
and then id plus,
Ah.
which is a path connecting the image of that id with that id. And then you can have a comp, which will be usual comp, and a comp plus, which will...
So that's almost the same thing, isn't it?
It is
Just
almost the same thing, but then you can have also associativity and associativity plus. I mean, I don't know, I think it's just, then it kind of looks really, you just keep these two,
Oh, you keep the thing in the plus.
keep two columns going, and you'll
Okay.
just be adding
Yeah, so,
plus to.
yeah, I've been choosing to use fiber because it represents, you know, a thing and an identity saying it's the right thing. But yeah, okay. Reasonable stylistic point, thank you. So, yeah, we're just choosing connected components. Next step up, I'll just write down the bits of the definition that differ. So definition-ish, two concrete category is similar, we only demand that things are zero truncated when we take a conf. So conf says zero truncated. So it means fibered in sets. So it means rather than just choosing whether to have components of morphisms or not, you're now choosing an arbitrary number of discrete copies of the connected components in the Hom types. So you can have some of the connected components a lot, some of them not at all, some of them once if you want. And that means we need more axioms. So that means now it's not enough to give ourselves identity and composition, as Vladimir was hinting. We're going to want to talk about unit laws and associative laws. Because now we need to demand that the structure we have respects, now we need to demand the structure we've given which tells us which components to look for the ids and compositions in, we need to demand that obeys associativity. Then after that, the type theory takes care of everything, but we do need to say that the sets of connected components we're using play nice. So I guess the axioms are, I won't bother writing them down. So we need unit L, unit R, and SOC now. The usual category theoretic axioms, we need little things, which we can either write as fibers, as I've done in my code, or we could write as pairs consisting of the left thing of a fiber and the right thing of a fiber, which is, a choice of thing and an equality saying it's the right thing. And then, three concrete will be again one truncated. So this is the disadvantage of starting counting at 0, not -2. I have to subtract 2 all over the place.
Well, actually, may I interrupt again? If you started counting from 0 there also, and instead of saying -1 truncated, you would say of H level 1, which is what is it called in the other library.
Okay.
Then here you would have H level 3, which would be perfect.
That's true. Yeah, I should get consistent, shouldn't I? Oh. So then you're going to add the usual two categorical axioms, the usual things you say in a bicategory, so you're going to have the pentagon and triangle identities. So the pentagon identity is the one that I drew way up there. The triangle identity is the thing you get if you try to work out what the appropriate coherence is for identities. And you can keep going. The definitions have the same shape and same stress as writing out definitions of higher categories. Just writing down definitions of any categories, that is. So yeah, so people understand why I don't explicitly write down the axioms for a three concrete category, because it's going to be ugly, and the axioms for a four concrete category, if you're going to write them down purely explicitly, are going to be extremely ugly and so on. But if you believe we have a good theory of n categories for small n, then we shouldn't be too worried about having a good theory of n concrete categories like that. So I should give you some examples. Why am I wasting your time on this? And the answer is there's quite a lot of examples. So, long enough, listener, I probably ought to go read them. So a stupid comment is any n-concrete category will give an n+1 concrete category. So you steal, each time you do this, you steal another level of tautological structure that was provided by the type theory for you and is all given by Raffles, and you make it explicit and you explicitly code in the Raffles. So, as I mentioned earlier, there's 0 concrete categories of things you care about. So there's types, sets, groupoids, finite sets, by which I mean fin, and so on. They're all 0 concrete categories, so that they're fun to work with. There are some decent 1 concrete categories. So the sort of baby example is delta is a 1 concrete category. I'll say something a bit stronger than this in a sec, but this will do for now. So delta is a 1 concrete category, and you can just do it explicitly if you so want. You can write down explicit models. So obj equals n, and then hom, so you can give a recursive model for the homs. And you just think, how do I recursively build up order-preserving maps of ordered sets, and you can sort of shove something in at the beginning in 1 of 2 ways, and that builds them up. It can't go wrong if you try it. And you probably want to take obj plus to be fin, so the map that takes a natural and associates the finite set with that many elements, and then you have some fun coding the actual meaning of your recursive model for morphisms, and then you prove some theorems, and it took me sort of a couple of pages of printed actor. So by the standards of things that people have done, this is not too hard. What's next? All AKS categories are 2 concrete. So you can... So somehow, the deal with AKS categories is that they're giving all the structure by hand. And the higher structure is trivial, so you can take obj plus to be constant valued at a trivial type. And you give all the structure by hand, and then, given that they just have hom sets, what you have is that the hom sets of an AKS category are fibered in sets over the point, because the point is the map, map of homs between a point and a point. So you've given all the structure yourself, and you just, for this one, you just want type to go away and not bother you. By a trick, so slightly better, by a trick, if automorphism groups, if all aughts are trivial, then they're 1 concrete. So you have to work a bit harder for that to give a good obj plus that makes that work, but you can do it. So that in particular recovers this one, which is your sort of favourite example of a category with trivial ords. So you can systematically write that as a one concrete category. Last ones, last examples. How much longer do I have, by the way? 3 minutes, something like that?
Wait a second. You have more because
Brilliant.
Because why?
no.
Isn't this the day we have just 1 hour in each room?
Well,
I'm asking, what is the time? Is that correct?
yes, that is correct. But
All
but you
right,
but you have until 1.
Good.
So
Okay. I might not use all that. Let's see. I'll be relaxed. That's the so types. So each individual type should be an infinity naught category, infinity groupoid, and we should be able to think of it as an infinity 1 category. And types form 1 concrete categories. So, I mean, a different claim to the category of types is a 0 concrete category. I mean, each individual type, i.e. X type, gives us sort of X, 1 concrete category. Again, that needs a bit of a trick. So you take the type of objects of X to be X, which looks like the right sort of thing to want to do for univalence purposes at least. And then you want to take, you want to take obj plus of X to be the sigma types. I'm sort of deviating slightly from Agda notation, I don't care. To be, so you want to take the representing type of an object X of X to be the type of path into X. And then you think a bit about how to compose those things, and of course, if you have a path in X, you can post-compose such identities with it, and then you spend a while checking that the resulting structure is one concrete, and it works okay.
wait. Good that we have 2 more minutes.
Yeah.
Could you can we have a look at that?
Can we have a look at
So
that?
you're saying let's take this gadget, which is a type, and it's actually a contractible type, as far as I.
Yep.
And so then the functions will be will have to be a subset of functions from that type to another such type.
Which is also contractible.
So these guys will be functions from one contractible type to another contractible type,
Yep.
and that is going to be contractible.
Solid point. I thought I proved this.
It seems like the kind of obvious choice of conf would only be as truncated as the equality types of X.
Yeah, I agree. There's going to be no conf.
Yeah, no, home is not good because home should be equality types, right? That's what
Yeah,
we want.
hom could be arbitrarily nice, and this could be unpleasant. So, shall I just retract my claim on that one?
Okay.
I do have another example of something that definitely isn't either. So it's not as if it's the first thing that doesn't work. So type star is not, so the category of pointed types is not n concrete for any n. And that's true for similarly hey.
So
Or-
the obvious way of trying to make type star concrete, so the obvious functor to type isn't n concrete for any n, or that there's no functor to type which makes it.
I mean, there's no strategy, there's no structure whatsoever of an n-concrete type on it. So I can't yet prove that internally. So I've got an external argument which requires asking whether some infinite list of types contains any that are inhabited. So the proof I have, I ask whether a whole bunch of types are inhabited. If none of them are inhabited, I say one thing. If they're all inhabited, I say something else. So, but I have no idea if this internalizes, but I think the slogan is I should stop thinking about type star. Okay, so a consolation prize for that pointed n types are n+1 concrete. So that's probably not too surprising. If you have pointed n types, you're going to have fairly pleasant Hom types, and it's not too hard to imagine that they'll give you appropriately truncated maps when you try to realise them like that. So okay, so this is clearly not a definition of infinitely one categories in any generality whatsoever. What's it useful for? Well, getting towards the end, so I'll start talking rather than writing. I think the one thing that's clearly useful about it is it does give you easy ways of constructing some categories. And if people are going to do a lot of work and come up with a better definition of categories, this had better map in and it better map in nicely. So, I'd like to advertise this to people who are trying to do better things than this as a sort of family of test cases. If you can't do this, you're not doing it right. The other thing I've been thinking about recently is how to use it for databases. So, the sort of work in progress on databases. So Spivak has suggested that you should think of a database schema as being like a finitely presented category. So I'll sort of draw an example of a simple database schema influenced by the real world to explain why this should be the case. So you have a bunch of employees, and employees all have managers, and they all have names, and I guess employees all have offices, and offices have addresses, and I guess employees may have dates of birth as well. So that's just a graph as described so far, but you really ought to think of it as a finally presented category rather than a graph, because you might want to impose constraints. For example, in your office, it might be the case that everyone's manager works in the same office as them. And in that case, you have the office of a manager is the same as an office, which is, a non-trivial categorical constraint, makes it not a graph anymore. And so Spivak wrote this, and he wrote a lot about how to do basic database operations, so inserting people, deleting people, and all that. That's all very handy, but it misses out the sort of fundamental observation about how you really do databases, which is that the stuff on the left is kind of different to the stuff on the right. The stuff on the right is going to be represented as a built-in type, whereas the stuff on the left is going to be represented by some ad hoc data structure, representing, some sort of list or table or something. So wouldn't it be nice if you could come up with some framework that contains all those things? So have some framework where you can explain what sort of object you expect each thing to be. And so, for example, you probably want date of birth to lie in a built-in type, and that type will luckily be, I'm sort of going to depend on this this example, but in fact this example is okay because it's going to be an n type for some n, and then we don't have a problem. And similarly, whereas employees is going to live in some kind of homebrew model of the category of sets, and that will hopefully also be an n-concrete category for some very small n. And so you want to have a category theory that allows you to have functors between, within your data structures as happily as functors without. And this seems to be a good start. I haven't done any database theory yet, but it seems to be the right language to start talking about. Does that seem like time up? I think it does.
Yep, pretty much.
Probably the least homotopy theory
Questions?
thing I've ever said.
Are there any sort of closure operations that any of these things satisfy? So I mean, can you make any construction? How is it slicing or?
Yeah, you can do some. Products is okay, for example. One concrete and above all have products. Slightly more exotic operations are okay.
Okay. So
Yeah, you may have sort of truncation hypotheses at various points, but so you can start doing those bits of category theory. What's a bit more annoying is functors.
yeah.
So trying to make n concrete categories into an m concrete category for any n seems fraught with pain.
Sure.
I need another idea from someone. Are any of you still alive?
That example of yours with types form one concrete category, I'm kind of, it sounds like there might be something interesting there if you think like maybe like n types form a minus one concrete. I mean, there is an obvious thing there, but there is a next to the obvious which may still be true.
Yeah, I think each n type will form an n concrete category or some similar adjustment.
Well, any n type will form an n minus one concrete category just because its home sets are n minus one types, and so it's by automatically.
Yeah, so
But I'm wondering if it may actually form an n minus two concrete category.
So I think that was my hope originally. So the trick you use here is to use Homs in again. If you take
Yeah, so maybe that's somehow.
Yeah, I think there are a few interesting questions about how far you can push it down. And it does seem to sort of be worthwhile insofar as you kind of, every time you push it down a level, you really are kind of decreasing the amount of complexity in a real life representation of something. You're giving more things to Agda and less to do yourself every time you do this.
What about something like a category of monoids? Can you make a version of that, or
If by
types with some other kind of algebraic structure?
monoid you mean set with a monoid structure, then I bet you can. And that would be an AKS category in particular, I should think. If you mean monoid objects in types.
Yeah, but
Well,
usual monoids will be one concrete, sorry. Right?
I mean, what do you mean by monoid? Do you mean sets with monoid structure or types?
Sets with monoid structure.
Oh yeah, that'll be two concrete at worst.
No, but it will be one concrete because home between monoids is a subset of home between sets.
Yeah, so agreed.
So it,
And
it makes
So what if I do
total
something
sense.
stupid? I just say, well, a monoid is a thing with a binary operation and an associator, and I don't bother to do any higher coherence.
that's probably okay. Yeah,
Yeah,
that'll same thing still works.
yeah. But then start trying to do higher coherence, then
Every time you add a coherence, you're going to make it one step harder for yourself, I suspect.
I mean, just for monoids, I mean, can we do the whole sort of static operator thing in
Well, this is what, when I said bright people have tried this and they're not done yet, this is what I mean.